The context of what we're doing is something that, I've been talking for a little bit, I guess, I know some, it's crazy, some of you don't think it's crazy, but it's this is, if we can use carbon to make materials on a very large scale, we solve a lot of problems. Right? So the idea is to have reactors that make a type of carbon, but then can we be made into fibers and other types of forms that can replace other currently used materials. And the carbon can come from a lot of sources. It can be fossil carbon, it can be renewable carbon, and if it's renewable carbon, because it would come from a biomass route, effectively is equivalent to doing carbon dioxide removal. All hydrocarbons, or all these feedstocks that we use to make carbon nanotubes contain hydrogen. And so we co-produce hydrogen with the carbon nanotubes. We never paid too much attention initially, but the last few years since we started talking about this, several people have noticed. And because of the properties of nanotube materials, so fibers, tapes, etc., we could replace, for example, copper and aluminum in electrification. We could replace steel and aluminum and carbon fibers in industrial materials. And if these materials are cheap enough, we could also build our environment with this. The other thing is that we know now that nanotubes in fiber can be recycled, and there's essentially a supply of these of carbon everywhere in the world, so we wouldn't have bottlenecks with supply chains and job security. So how would this look like? Really, you need to think about it in 3 steps. One is you gotta go from your hydrocarbons to the carbon you want in 1 step. You really, really want only a chemical reaction if you want to do this on a large scale, because that's where you're gonna spend a lot of energy, and if you have a sequence of chemical reactions, that's gonna hit you. Then that material has to be usable for scalable processing, whether it is a stretching of a direct spun fiber or a wet processing. That's where you want to differentiate into shapes, and then after that you want to differentiate further into structures and applications. And right now I think that the only precursor that can do this is carbon nanotubes, but not just any carbon nanotubes. I call them fiber grade carbon nanotubes. So the right precursor has to be longer, high aspect ratio, high quality, either few walled or single wall nanotubes. And so you could produce a few precursor grades in large plants, like we do with the polymers, and then the differentiation will be done downstream in processes that have lower energy intensity, lower capital intensity. Now, we did LCA and PA of nanotube production right now using data from reactors we have in the lab. And synthesis dominates the embodied energy of the material. And the reason is that even though conversion is getting to be pretty reasonable, this is done with a 22% conversion of methane to carbon nanotubes, the dilution is low, is high. So typically groups are using 2 to 10% maximum feedstock concentration to control the reactions. So the reaction energy efficiency is about 2.5–3%, which is much better than what everybody was doing years ago, but it needs to be increased. And so we need to understand the reactors to do this. So most of my talk is going to be on reactors, and I hope it's okay. So there's been a lot of work on reactors, more or less for continuous flow CVD, which seems to be the most likely route to make high throughput fiber grade materials. You come in with precursors, maybe some gases, process gases, etc. The reactor furnace wall is at about 1200 C or higher. Residence time is in the few seconds to tens of seconds. And when what comes out is the nanotubes, some catalyst attached to the nanotubes, amorphous carbon, etc. The picture in general is the following. The catalyst precursor has to decompose, form nanoparticles. When the nanoparticles are formed, the carbon has to be activated out that if you want to study reactors, even at the lab scale, you need to put a lot of attention to chemical engineering. And I think this was a hard lessons for us. We didn't realize that so much was needed in terms of understanding delivery systems, understanding the flow mixing, the need for feedback controller, etc. So I'll show you a few things that I think they're already done in industry, but I don't think they have been published yet. So the first thing is typically ferrocene is delivered by gas phase sublimation in a variety of configurations. Now, what we ended up having to do was using a packed bed with particles that prevent gas entrainment. But even with that, we realized two things. One is the assumption that everybody seems to be making is that at the exit of these sublimators, you attain equilibrium, so your gas is saturated. So saturated gas would be over here. Now, we figured out a way, we developed a way using an acoustic sensor to measure the speed of sound in the gas to measure the concentration of ferrocene in the delivery stream. And so we can actually, and this is the way this was all calibrated, but once you calibrate, you realize that as you go, especially higher in temperature, no matter how well you control your temperature bath, you have fluctuations, and you're also not even close to your nominal delivery rate. You can be 20 to 40% off. So there's two problems. One, we're assuming ideal saturation, and we don't have ideal saturation. The second thing is that we can drift. However, once you have a sensor, we can have a feedback control system. And so now what we're doing is we're running with feedback controller. And so downstream of the evaporator, we're measuring with this acoustic analyzer, we're measuring the concentration, we determine an error, and then we compensate with changing the gas flow to the evaporator. And so what we saw is initially this is why the uncontrolled system. Once we controlled it, it actually got worse. And the reason we got worse is we were controlling only the ferrocene and not the thiophene, which is our catalyst. So, but once we put controllers on both streams, catalyst and co-catalyst or co-precursor, then we got a much tighter control on the system. So this is showing productivity measured in different runs of different days in the reactor. So it's important to do this because when you're actually trying to look for relatively small changes and improvements, you need to be able to control your system well. The second thing is this system delivers very, very dilute concentration of gases. So for example, at 63C, which is pretty typical for running a sublimator, the vapor pressure of ferrocene is a few hundreds of kilopascal or an atmosphere. Per kilopascal. And so we switched to actually using a bubbler. So we melt the ferrocene, so we stay a little bit above the melting temperatures, and now at this point we have high vapor pressure, which means that before on a sublimator we need 1,000 to 1,500 skims to deliver, let's say, 40 milligrams an hour of ferrocene. Here now we can do it with a few skims of gas. And the delivery is very stable. So in this case, we actually don't need to use the feedback controller because, first of all, it's easier to saturate the gas with ferrocene when you're doing it through a liquid bubbler, and the second of all, the delivery system is important. So this is why is this important? One is if you reduce by 3 orders of magnitude the gas flow rate to deliver your catalyst, it really decouples the catalyst delivery from the process gases. So a lot of these processes in CVD are using large amounts of gases, especially non-reactive gases, just to carry the catalyst. And so you can't intensify. So now this is out of the way, and you can intensify and then look at whether there are other physical issues. Stable delivery, the other thing is a high pressure operation. Now, this equation here works for both sublimation and bubbling, and that's the pressure of essentially the reactor. If you're at 1 atmosphere and you go to 10 atmospheres, which is what industrial systems seem to be operating at, you can't deliver with the sublimator. Whereas with a bubbler, you can still deliver because your vapor pressure is high. Now that's the first part. Second part is how do the reactors actually work? So Sang-Min Kim a few years ago introduced a deep injection concept where he showed that injecting deep into a reactor increases significantly the productivity of the reactors. What's interesting is if you look at Windows 2004 paper, Windows was injecting deep in the reactor, but there's no mention of that. So we studied this a little bit more, and we realized that it's a combination of two things. One is the depth of the injection, and the other one is the Reynolds number at the exit of injection cannula. Everybody thought these reactors are low Reynolds number because they're calculated Reynolds number with the diameter of the reactor. But what controls the fluid dynamics is the Reynolds number with the diameter of the injector, and there is a ratio, of course, of the two diameters. So you form a jet here, and the jet length is the Reynolds number based, so essentially it's a momentum of the gas that's coming in times the reactor diameter. And for the conditions that we are in CNTs papers and similar papers, the optimal jet length is roughly the heated length of the reactor. And what seems to be happening is that the depth of the jet controls productivity. So what we did is we substituted argon, which was what Sang-Min had used in his original paper, with nitrogen, which is about the same molecular weight, so the same density. And we got about a production rate that was essentially independent of Reynolds number. We switched to helium. Now helium is a lot lighter, so we were keeping the residence time constant, but now we're going from a heavier gas, which is argon, to a lighter gas. So this is full argon, this progressively is less and less argon, and that's fully helium, and plus hydrogen and methane. And what you see is your productivity starts going lower, and your jet is getting shorter, to the point that over here, you almost don't have a jet, and most of the reactor is operating as a flow. Now, we also tried to substitute with hydrogen, and we got further deflection of the reaction because of chemical effects. So what seems to be happening in this high productivity reactor configuration is that the reaction is happening at the interface between the colder jet that's coming from here, and it's colder but not cold because the cannula couples radiatively to the reactor walls and acts as a preheater, and the gas that's transported backwards from the recirculation, also this gas has activated carbon, so has C2, and so that's where the reaction seems to happen here. Now these reactors were horizontal. We thought, what happens if we flip them and we put them vertical? And so now this is the difference between the vertical reactor, so gravity is pointing to the right here, and that's the horizontal reactor. This is what happens at high Reynolds number, so we're using nitrogen, and this is lower Reynolds number when we're using helium. A high Reynolds number, what you see is the flow becomes symmetric. A low Reynolds number, interesting, the flow is almost the same in the two cases. Why is that? Well, the jet length is independent of orientation, but the deflection length of the jet depends on the Richardson number. And the Richardson number is actually almost the same in the two reactors. It's a little bit higher in the case of using helium, because helium heats up faster in the cannula. And so it turns out that when you have a high Reynolds number injection, your jet length is longer than your deflection length, and so you see the jet deflecting in the horizontal configuration but not in the vertical. When you go to lower Reynolds number, your jet is shorter. Now the jet is shorter than the deflection length, and now essentially the fluid dynamics are almost the same. There's a small difference at the exit. That's due to the fact that the gas starts cooling, and in the horizontal configuration, the colder gas stratifies at the bottom and makes a recirculation there, and that causes the forward moving gas to move to the top of the reactor. That has an effect. we'll talk about later. Now, when you normalize by production at the high Reynolds number, the two curves are essentially on top of each other. If you look at it, they're not normalized. What you see is a productivity gap of both high Reynolds number and low Reynolds number. Now, this one you can explain with the fluid mechanics, this you can't, right? It's the same fluid mechanics, so what's going on here? Now, one thing that you see when you look at the reactor from the bottom, from the end, you see that the sock that you form, an empty sock, stays more or less coaxial in the vertical reactor because the flow is relatively symmetric, but it moves up because there is a recirculation at the bottom of the reactor of cold gas. So that's one difference. The other thing that we did after we did all this study, we realized that we're not using the same tube for the two reactors. We're just using two tubes from the same manufacturer, the same diameter, and the same composition, but we had used one tube a little bit longer. And so it turns out that actually over here, if you swap the tubes, you can get the difference the wrong way. That's how nasty these systems are, okay? And we almost didn't do that check. And I don't know if any referees would have picked it up. So in terms of tubes qualities, there are very little difference. The main difference is that for length, the tubes made in the nanotubes made in the horizontal reactor are longer than the nanotubes made in the vertical reactor at high Reynolds number. And at Reynolds number, what you see is that the vertical reactor has, if you look at the residence time in the vertical reactor, there is a tail that comes from the asymmetry of the flow, and we think that this is probably why the horizontal reactor makes longer tubes than the vertical reactor. But in terms of other things like G to D ratio, selectivity to good carbon, etc., there seem to be very little differences. Now, another thing is that these reactors may actually undergo instability. If you try to calculate the flow at high Reynolds number and you really push your solver, you realize that there's no steady state. And in fact, this is averaged over about 15 seconds. So you have a loss of this axisymmetric flow. Again, it looked like the Reynolds number was low, but if you calculate it with the canyon Reynolds number, it's not so low. It's about 590. So you can actually do a flow stability analysis. We did this now initially for isothermal case, so that it's a little bit simpler. And we see that as we grow the Reynolds number, at some point there is a hot five propagation. In the isothermal case, where this geometry is about 170, and so your branch, your axisymmetric branch becomes unstable, and you have multiple solutions that are time dependent. Now, you go back to the literature, which we did, you realize, well, this is kind of known for jets. But again, in this context, we haven't really realized it. Last couple of slides are on some things that happen in these reactors. What we see is we're making very high G to D ratio nanotubes, over 50, and as produced, they're not spinnable. And we only have to remove a few percent of carbon. And what's going on? And what we think is happening is the hypothesis that we have a secondary deposition of carbon in the downstream section of the reactor. I spoke a little bit about this yesterday in the talk I gave for Adam Boyce, but we work with Adam Boyce, Chris Rees, and Audrey Danner, and what we did is we took tubes that were purified and so could respond, and we put it in a tap reactor where we could control the deposition of acetylene or ethylene on these nanotubes. And what we saw is that acetylene deposited catalytically faster than in the baseline case if we use nanotubes that have the catalyst. If we use nanotubes that did not have catalyst, the ethylene deposited faster on the nanotube surface. And so what seems to be happening is at some point in the reactor there's some secondary deposition of carbon that coats the nanotubes, does not change their J to D ratio, but makes them not spinnable. And so finally, to address the spinnability, we worked with Maurice Terrones, and we asked, is there any signature in TGA that we can get that will tell us how long do we have to purify for? So here what you're seeing is how much mass we're removing in oxidative purification of as made nanotubes. The Raman is not changing, you can't pick this up. Every 2 hours we're removing more or less 1% of material, and what it looks like, the apparent aspect ratio is dropping, but this initial drop is not because the tubes are getting shorter, it's because the tubes are not soluble and make, or poorly soluble, make superstructure, and then they become soluble. Now the analysis is based on doing TGA at various temperature and various rates, and then measuring the activation energy of what you are taking out. And what we see after 6 to 8 hours of purification, we see a maximum in the activation energy of the material that's being taken out. And so from that, we were able to determine from not just by trilateral but by TGA, what's the optimal window for purification. So in this case, a 6 to 8 hour purification is what you need, because you remove some of this amorphous carbon that's deposited on the nanotubes, and you don't carry it so much that you start shortening the nanotubes and losing material. And when you take these and make fibers, you see that actually your best fibers are the ones that you made after 6 to 8 hours of purification. And if you purify further, you start losing particularly strength. So, okay, I'm 2 minutes out of time, sorry. Thanks.